All right. So yesterday we started our second lecture module, which apparently talks about the logic and proportional calculus. So we first of all motivated like why and how it all got started off. Okay, so basic motivation behind studying the logic or proportional calculus came from early philosophers and mathematicians who wanted to formalize how do you say some statement is correct, how do you say some statement is wrong, how do you find a good proof, you prove something and say this proof is correct, or how do you oppose it and say it's incorrect. So this all field developed from those concepts, and then we saw what is a basic proposition, right? So any declarative sentence that we have, which basically discusses or declares a fact, but with a condition that it can either be true or false but not both, or there is no ambiguity, such a sentence is what we call as a proposition. Okay, so any sentence where you can clearly demarcate whether it is a true statement or it's a false statement, such kind of sentences are known as propositions, and there is no scope of ambiguity, right? And then the value that this proposition takes is what we call as the truth value of that proposition. And there are just two possible truth values: either it can be a true, which is sometimes represented by a 1, or it can be a false, which is represented by 0. So that is what you have as your proposition. Okay, so anything which is unambiguously either true or false is your proposition. And then study of all such propositions and how do you infer things from it is what is known as proportional calculus, right? After that, we discussed that a proposition can either have a true or false value, but in general, like the various applications where it is used, whether it's Boolean algebra, whether it's design of circuits, in general, you never see a single proposition. You always see combination of propositions. Okay, and such a combination is what is known as a compound proposition or a compound statement. Okay, so a compound statement was nothing but when you have more than one propositions connected together using some connectors, right? And then we studied various operations on the propositions, first of which was a negation operation, which is very simple that given you have any proposition P, the negation of P is simply the opposite of P. So if it takes value true, it would be false, and vice versa. So basically very similar to the set operation complement. Okay, so if any value or any statement you make, its negation is simply the opposite of that statement. The other two connectives that we studied, which are very useful in making your compound statement, was conjunction and disjunction. Okay, so you had conjunction, right, and you had disjunction, which are popularly also known as and or, right? So when we say A and B, it's very similar to the set operation intersection, right? So basically, what we mean is this value will be true only when both of them are true. If either one of them is true, it will not be true. Like we have in set operation, the intersection operation, only those values are part of the intersection set which belong to both, right? If it's in one of them, then they don't belong to intersection, right? Whereas in or, it is basically similar to your union operation, that is it should either belong to A or to B or to both, or in general if either one of them is true it will be true. Okay, so at least one of them has to be actually true, right? And that is where we had ended our discussion. So in general we had discussed this disjunction or can also be of two types, right? So you can have an inclusive or, which is exactly the or we studied, that is uh, either of them should be true or even both can be true. But there is other variation of this known as exclusive or. And what was special about exclusive or? Anyone recalls? Yes, class? Sorry? Can you please repeat? Or you can write in chat. Exactly. Only, yes, only one of them should be true, not both, right? So let us continue with these connective operations. So today we'll try to see more of the connective operations and basic logical operations, and study things like what are converses, what are inverses, how do you make two statements equal. Okay, so let us start from there. Okay, so as we already discussed, that when we talk about disjunction, there are two types of disjunction. One is an inclusive or, which is exactly same as your normal disjunction or normal or. That is, we say P inclusive or Q basically means either P or Q or both, right? So all three of them are included. Or in other words, we want that at least one of them should occur. At least means it can even be two, right? But when we say P or Q but not both, you exclude the situations where both are true, right? So such kind of or is known as exclusive or, wherein exactly one of the two alternatives occur but not both. Okay, and it's very famously known as XOR. Okay, and it's very important for us as computer science students, because as you will see in eventually all of your courses, since we all deal with binary numbers, so XOR is the only operation which can be applied there. Okay, in general, when we talk about numbers, right, we see various kinds of arithmetic operations. You see addition, subtraction, but when we come to binary numbers, 1 and 0, okay, so addition, subtraction all boils down to XOR. So XOR is a very important operation for us as computer science IT students. Okay, and now what is XOR? XOR simply means those situations where exactly one of them is true. Okay, so if I have to make a truth table of XOR or exclusive or, how can I make that? Okay, so first of all, whenever we have two statements P and Q, the XOR of them is normally denoted by this symbol. There's the addition inside a circle. Okay, and this is true when exactly one of them is true. Okay, if both of them are true, then it would be false. Okay, so if I have to make a truth table of this, can you help me to formulate it? So I have four possible combinations. Okay, so what should be the answer if I write true, true? Okay, remember what is exclusive or? It is true only when one of them is, exactly one of them is true, right? So if both of them are true, then it is false, because as we said, we are going to exclude the both case. What about true, false? Very good. What about false, true? It is also true, because only one of them, exactly one of them is true, so both of them are true. What about last one? No, Zishan, it is also false. So whenever, basically, a simple way to understand XOR is whenever you have different values, you have a 1 or true, and whenever you have same values, you have a 0. Okay, is that clear? So this is your exclusive or. Okay, and as we already made the truth table, it is true only for the cases where exactly one of them is true. Okay, if both are true or both are false, it will be false. So whenever the two values are different, only then it is true. For similar values, it is always false. Okay, so these were the two kinds of ors. One is an inclusive or, which is the general or disjunction we study, and other is this exclusive or. Okay, and as I mentioned, in computer science, when we deal with only binary numbers, all your arithmetic operations actually reduce to XOR. Okay, so this is an important function to understand. Okay, in general, whenever we in this lecture module we use or, we basically mean inclusive or. Okay, at any point of time, if I want to refer to exclusive or, so I will exclusively write XOR. Okay, so or alone means only inclusive or. Okay, so is this clear? The two types of ors? Yes. So let us move ahead. Okay, so now we finished our basic logical connectives, which were disjunction and conjunction. Okay, now let's move to another logical operation, which is known as conditional statement. Okay, let's try to understand what it means, how it works. So, given two proposition P and Q, the conditional statement is denoted by this P arrow Q. This is pronounced as if P then Q. Okay, so this statement is written as if P then Q. And how do you evaluate it? The conditional statement of P implies Q is false when P is true and Q is false. Okay, and in all other cases, it is true. Okay, so this is how its truth table is formed. So whenever you have P, just P, that means the first statement which you check with if, whenever that is true, okay, and the second statement is false, only then it is false. For all other cases, it is always true. Okay, so when your checking statement P is true but Q is false, only that is the case where the conditional statement is false. Okay, or to simplify it further, when we have these two statements P and Q, this P or the first statement has a special name. It's known as hypothesis or antecedent or premise. Okay, so basically, what hypothesis you take to come to some conclusion. So, your first statement is your hypothesis, the hypothesis you try to make. Okay, and the second statement is what you derive at or what is your conclusion. Okay, so in general, whenever your hypothesis is true, but it turns out that your conclusion is false, then your implication is false. Okay, otherwise, every time it is going to be true. Okay, so it's a slightly different truth table. You got to understand what is going on. Okay, and it's a very powerful logical operation. Okay, so what is a conditional operator? Conditional operator has two propositions, one of which, the first of which is known as a hypothesis, and second is known as the conclusion. That is, what conclusion do you take after assuming some hypothesis? Okay, and the way it works is it's going to be true for all conditions except when the hypothesis is true and conclusion turns out to be false. Okay, in general, whenever we discuss P implies Q, it is actually to assert the fact that Q is true whenever the condition P holds. Okay, so whenever your condition Q is true, your condition Q is true whenever your hypothesis or P holds. Okay, and often it's also known as implication. Okay, that P implies Q. Okay, so this is your what you call as the conditional statement. So in general, there are various ways in which this conditional statement is expressed. Okay, so sometimes it is written as if P then Q, or if P comma Q, or P is a sufficient condition for Q, Q if P, and various other versions. Q when P, A is a necessary condition for P is Q. Okay, so this is something which we'll see frequently. Necessary and sufficient condition. Okay, so let's try to understand what do we mean by necessary and sufficient condition. Okay, so when I say P implies Q, P is a sufficient condition for Q. Okay, that means if P holds, then we can make a decision about Q, right? Similarly, the vice versa is true. The Q is a necessary condition for P. Okay, so if you have to remember the relation between P and Q, then P is a sufficient condition for Q, and the opposite one is its necessary condition. Okay, so there are a couple of other phrases in which you can see this condition, so you can have a look at them. Okay, let's try to see an example so that we understand we are following the conditional statement. So suppose you are given two statements, two propositions. So first one, your P statement is Maria learns discrete mathematics, and Q statement is Maria will find a good job. Okay, now can you express different forms of the implication statement of P implies Q? Just give it a try. Okay, you can use all any one of A to M for this representation. Okay, you are given two propositions P and Q. You need to write an English statement P implies Q by combining the two using any of these equivalent statements. Very easy class. You just need to try and use one of these conditions. Yes. Yes, Rituraj, you can speak up. Okay, point C. I'll do that. So we are going to study necessary and sufficient condition in detail when you go on proofs. But for now, so all this A to M are basically the equivalent versions of saying P implies Q. Okay. Now, what is this C1? So when we say, so there are two statements normally that we, two conditions that we normally check. Okay. One is a necessary condition. Okay. Necessary condition means, so let me also bring the truth table here. So that will make it easy. You have true, true, true. You have true, false, false. You have false, true, true. You have false, false, and true. Right. So when we talk about these conditions, necessary and sufficient condition, so there are in terms of implication, what we say is the first one, the hypothesis, is a sufficient condition for Q. Okay, so what do I mean when I say that P is a sufficient condition for Q? Okay, what I mean by this is what we said here, that Q is going to be true on the condition that P holds. Okay, so whenever P holds, P has some value, Q is going to be true. Okay, which you can say in the sense that if any of my proposition which stands for P is going to hold, then Q is going to be true. It's a sufficient condition to hold, right? But what about the conclusion or antecedent? Can I have any inference of conclusion based on the hypothesis, right? Can I say anything of Q by referring to its relation with P? Okay, that is what is implied by F, that if P is a sufficient condition for Q, actually necessary condition for P is Q. Okay, so if P is just a sufficient condition, but but when we talk about the opposite sense, necessary condition for P is Q, that Q has to necessarily hold if P has to be true. Okay, so it may not be very obvious here. We'll visit it back when we discuss proof statements. Okay, but here for now, if just to have an idea, what you need to understand is neither of them are independent of each other. Okay, the only difference comes in the way which one holds importance. Okay, so you can see from the truth table itself, hypothesis holds importance in the sense that whenever it is true, that's the only and the other conclusion is false, that's the only condition when your implication is going to be false. Okay, and that is where it implies the condition of that basically the necessary condition for P is Q, because only the case where Q is false and your P is holds, it's true, it will be false, right? If you look at the under other condition where Q is false, but there P also does not hold, right? So it's not a determining factor. Only when your P is false and you sorry, Q is false and your P holds, it's the condition your implication is false. Okay, which actually highlights the fact that it's a necessary condition, you cannot do away with it. Okay, but if you come back to the other false case, since both of them are false, so even if your conclusion was false, since the proposition or the hypothesis also did not hold, so it did not determine your implication. Okay, so that actually highlights the fact that the necessary condition for P is Q. Okay, is that more or less clear, Rituraj? We'll see some more examples when we go to the proof techniques. Okay, yeah. So, so I Sorry, I missed the answers. So some of you have written. Okay. So only Shriya wrote the English statement. Please, I want others also to try it. Okay, Maria will find a job when Maria learns to speak once. Yes, that's perfectly okay. So she tried to use this one, E, right? Shriya, you use the E one. Q when P. Very good. Ankita, Maria will find a job unless she finds. Okay, Maria will find a job if, what, unless she learns to speak maths. Okay, so probably you use G, Ankita. So you can use all possible combinations here. Okay, so I assume everyone has taken its step. So there are various possible ways you can state it using any of those following, and all these A to M are actually equivalent. Okay, but I'm not going through each one of them because this is something which we'll see in detail throughout this lecture module, and we'll see all of them are equivalent. Okay, that is P implies Q is same as when you say Q unless not P, or it is same when you say P only if Q. Okay, we'll see all of them are equivalent. Okay, and in terms of English statement, you can just use any one of them or rewrite it. Okay, now so you saw various versions of P implies Q, right? So which basically is if P then Q, right? Have you ever seen this notation ever in your computer science, any of the courses, programming courses? If something like if P then some statements or something. Have you ever encountered this? If if then kind of statements. Have you ever encountered it? Exactly. If else that you study in programming, right? So is there some relation, right? Because that is also something similar, right? We do in loops. If some condition is true, then the statements we write will hold, else some other statements will hold, right? We frequently do it in programming. So is there some relation with this, right? So the if then construction that you use in programming language, please note that it is very different from the logic. Okay, so it's not same as what we do in logic. Okay, in if I write if P then Q, okay, so we know what are the truth tables. When P is true and Q is also true, then your implication is true, right? Similarly, the case when this is true and this is false, it's false, right? But same thing does not happen in programming language. It is totally different. Okay, in general, what we have in programming language is we have some statement. If that is true, then the programs or commands we run, they will be executed, and if it is false, then it will just skip them, right? Like if you recall the simple example, suppose I have a variable x equal to 0, and if I execute this statement, right, what will happen? Okay, I'm talking about the context of programming languages. Yeah, so what will happen if I execute this statement? What will be the value of x? Yes, class, what will be the value of x? Come on, class, it's a very simple if else question. So I have a variable x which has a value 0, and the question is what is the value of variable x after this statement is executed? Okay, so I'm talking about programming language. Simple, it's 1, right? Because if 2 plus 2 is 4, this is a true statement, right? In general, whenever I use a equal to, it's always true. If I have to check something, then what should I use instead of a equal to in programming language? So there's a difference between equal to and equal to equal to, right? It is an assignment operator. It's when you check for something, right? So this is always true. So definitely it's going to increment and x will become 1, right? But suppose I tell you that it's not a programming language. We are talking about this statement in logic. Okay. Then can you say anything about it? Let me repeat my question. So you said, when if I'm talking about it in context of programming language, the value of variable x will be 1, right? Because it's a simple if else. The statement is true, so x will be incremented. Now if I am considering these statements under the context of logic, what would be the consequence? Or can I even say something about it? Okay, so I have, so this is my proposition p, and this is my proposition q. So it's like P implies Q. Right? What can you say in context of logic about it? Excellent, Hasi. Okay, so that's where you need to be active all the time. No, that's where you need to be active all the time. Remember, x equal to x plus 1 is not a proposition. Why? Because it's ambiguous. You don't know what is the value of x. Right? Assuming I had said this is the only thing given to you. Okay, now not what I had mentioned before. Okay, but if I tell you that x is 0, okay, and you include it, then can you say something? Okay, then can you say something? So Dhananjay says false. What about others? Last little bit of brainstorming. It's not difficult. Okay, so I have now given you p, and I have given you q and made it a proposition by putting the value of x as 0. Okay, now you need to tell me what will be the value. Can it be evaluated? What will be the value? Okay, okay, so let us see. Okay, so if p, where p is 2 plus 2 is 4, so it's definitely a true value, right? Then we have x equal to x plus 1, okay, where x is 0, so we have 0 is equal to 0 plus 1, that is 0 is equal to 1, which is false. So I have true, false. So P implies Q. Okay, so this is the same case, the unique case where the implication is false, right? So it is false. Okay, is this clear? See, I threw a question three way to you. Okay, first I said it is a programming language in context of programming language, right? Then what should be the answer? Okay, so in terms of programming language, simply x will be executed, and that's what you will get. X is equal to 1. Then second thing I proposed was that assuming just these conditions are given to you, the only this if and else condition is given to you, what will be the result? Okay, in that case you cannot give any result because x has no value defined, and this second part is not a valid proposition, right? So you cannot say anything. Then the third part was, if I suppose give you a value of x, that means I make it a valid proposition, then what is the result? In that case, you need to see what is the truth value of p, what is the truth value of q, and then see what will be the result of p implies q. Okay, is this clear? This example is clear? Yes? Is this clear to everyone? See, this is where you have to be active, right? Like whether you have, in future, if you appear for interviews, you appear for some competitive exams, you will never see topics from just questions from one topic. It will always be a mix and match. So you have to keep your, eyes and ears open, that what we are hearing and seeing, it will all be connected. Okay, great. So let us now then move to the other part of logical connectives, and a very interesting feature of logical proportional calculus, which are the three important variations of a proposition: converse, contrapositive, and inverse. Okay, let's try to understand what each one of them means. Okay, so in general, whenever you use this conditional statement P implies Q, there are various versions that you can actually form by this implication. Okay, the three popular versions are converse, contrapositive, and inverse. Okay, so let us see what does it mean. So if I have a statement P implies Q, the converse of it simply means flipping the two variables. That is, hypothesis becomes the conclusion and conclusion becomes the hypothesis. Okay, this kind of flip is known as a converse. Okay, it's little confusing, so please pay attention. So what is a converse? Converse is simply flipping off the conclusion and the hypothesis, or in simple words, flipping off the first and second proposition. Okay, second is contrapositive. Okay, so if I have P implies Q implication, contrapositive means two steps. One, you flip the hypothesis and the antecedent, or hypothesis and the conclusion, and also take their negation. Okay, you also take their negation. Okay, two steps. You flip the two statements, first becomes second and second becomes first, and then also take its inverse, sorry, the negation. Okay, similarly the last one is known as inverse, which is if I have P implies Q, you simply take its negation. Okay, so what are the three versions we have? Okay, on one end we have so you have P implies Q. On one end you have a converse. Okay, converse means flipping the positions of your hypothesis and your conclusion. Okay, that is Q implies P. On the other end you have inverse, which is taking the negation of them. Okay, now if you combine both of these operations, flipping of antecedent and the conclusion, as well as taking the negation, that is known as your contrapositive. Okay, so these are the three basic versions of conditional statements that you can make out of your simple if else statement. Okay, and out of all this, you can verify yourself using the truth tables. Contrapositive has same truth value as P implies Q. Okay, and you can check for yourself that these are equivalent. Make the truth value of both and you'll see for yourself that they are equivalent. Okay, let us see some examples to understand it better. Okay, so suppose I give you the following statement. If he studies maths, then he is a genius. Okay, so I made two propositions. So he studies math is P and he is a genius is Q. Okay, now can you tell me what is the converse of it? Okay, it's in the simplest form, in if then form, so you should be able to do it easily. So you need to flip the parts. Very good, Dhananjay. So now the two parts will get flipped. Hypothesis becomes conclusion and conclusion becomes hypothesis. Okay, so now you consider the hypothesis that if he is a genius, then he studies maths. Okay, excellent. So you have if he is a genius, then he studies maths. Okay, by the way, it's not necessarily true. I'm just taking a hypothetical example. Okay, what about contra, or let's do first inverse. What about the inverse of this statement? Inverse of this statement? Inverse simply means you don't flip the positions, only take their negation. Excellent, as simple as that. Okay, you just need to introduce a negation part here. If he does not study maths, then he is not a genius. Okay, and what about contrapositive? Okay, remember, now you need to do both the operations, flip them up as well as take its negation. Excellent, Rishita Dhananjay. If he's not a genius, okay, so first I flip it and I also negate it. If he's not a genius, then he doesn't study maths. Okay, so it may sound very silly here, but as we'll see more advanced form of proof techniques, these are very frequently used. Okay, we'll hit them again and again. Okay, so let us see some more examples. Okay, now it's slightly different. The next example I am giving you is slightly different. Okay, first of all, is was this example clear to everyone? uh, P implies q and its inverse, converse, contrapositive. Yes, class, is this clear? Okay, there's a very subtle difference between all three of them, so you should be careful about that. Sure, Zishan, I will repeat. Okay, so in general, why are you first studying it, Zishan? Okay, so what we are studying is, we saw in previous slides what is an implication, okay, which is normally seen in this form: if P, then Q, right? Now what we are studying on this slide, what we introduced was three various versions of implication, which you can extract from the simple implication of if P then Q. Okay, and what are these three versions? The three versions are known as converse, okay, inverse, and something called contrapositive. Okay, what are all three? They are nothing but implication statements only. Okay, which means you will have some two propositions and there will be an arrow or implication between them. Okay, but these are various versions of it. Okay, now how do you get these versions? If I have a simple implication P implies Q and I ask you to make its converse, okay, so how is converse defined? Converse is defined by, like if I give you a set and I ask you to find its complement, how do you find its complement? You take all the elements which do not belong to the set but belong to the universal set, right? Similarly, when I find the converse, what I do is I make a preparation by wherein I flip my antecedent and conclusion. Okay, so we know that for a simple implication, P is what? It is my hypothesis, and Q is my conclusion, and both of them are not equal, right? If I flip them, P implies Q does not necessarily mean Q implies P. Do you agree that, Zisha? That if I write P implies Q, it is not same as Q implies P. That is, if I flip them, it's a different thing, right? So now when I have to create a converse conditional statement of a given implication statement, how do I do that? I flip them. By flipping, I mean my hypothesis becomes conclusion and conclusion becomes hypothesis. Okay. So if I give you a statement P implies Q and I ask you to take a converse of them, the way you can do is you can switch the places of your hypothesis and your conclusion. Okay. Like here, I had given you a statement: if he studies maths, then he is a genius. So my hypothesis was that if someone is studying maths, then my conclusion was he is a genius. Now for converse, I need to flip it. Okay, so that's what we did. So now my hypothesis becomes that if some person is genius, then I would conclude that he studies maths. Okay, so that is how you make converse. Okay, is converse clear? It's simply flipping the hypothesis with conclusion, right? Now what is then contra let's first take inverse. Okay, so one was converse, which is flipping hypothesis and conclusion. Second is inverse. Okay, inverse is like you have inverse of function, inverse of set. It's simply taking the negation. Okay, so if I have an implication P implies Q, its inverse is simply not of P implies not of Q. Okay, so like in this case, I'm not going to flip hypothesis or conclusion, I'm just going to add negation to these statements. Okay, so I can write its inverse as, if he does not study maths, then he is not a genius. So by introducing not, I introduce the negation of these statements. Yes, exactly. Converse is flipping, inverse is opposite in the sense you negate it. Okay, and contrapositive is mixture of both. You flip them as well as take their negation. Okay, So it's like flip them, make genius the hypothesis and studies maths the inverse, and take its negation. That is your contrapositive. Okay, is that clear? All three of them, Zisha? Okay, great. Okay, and do check this for yourself that actually contrapositive has same truth table as your final implication. This is same as saying not of Q implies not of P. Okay, check it using the truth table. Okay, is this clear now to everyone? Converse, contrapositive, and inverse. Excellent. So let us move to this example, which is not clearly written in if and then form, but just another variation of conditional statement. Okay, and the statement goes as follows: the home team wins whenever it is raining. Okay, so there are two propositions hidden inside it, but they are not directly written in the form, if this, then this would happen. Okay, now if I ask you to find its converse, inverse, and contrapositive, always the first thing you should do is to bring it in the simple if then form. Okay, that will make your life easier. Okay, and then you can easily find all converse, inverse, and contrapositive. Okay, so can you first rewrite it in if and then form? Yes, class, can you just rewrite it in the if and then form? Okay, because it's always good to write in if and then form, because then flipping it is becomes easy. Okay, excellent, Dhananjay. If it is raining, right, you can see from this clause, right? So this was another way of denoting. As I said, we'll be coming back to the slide again and again. So if I have P implies Q, one of the alternate way of saying it is Q whenever P. Okay, and that is what we had here. Whenever it is raining. Okay, so that means it is raining. It is raining is your first statement, or it is your hypothesis, and home team wins is your conclusion. Okay, so that is why I can, if I have to write it in this form, I can write if it is raining, then the home team wins. Okay, so this is very important, how you map it back to if and then form. Okay, let me just repeat it in case somebody missed it. Okay. So in general, when we have P implies Q, there are various, we studied that there are various ways by which we can write it in English statement. Okay. One, the most simplest way is to write it as if P then Q. Okay. But some more equivalent ways are whenever Q, whenever P. Okay, this is also equivalent to saying this. Okay, so whenever we use this word whenever, so the first proposition that is written is actually a conclusion, and the second proposition which is written is a hypothesis. Okay, so now in this statement, okay, you can see which one is P and which one is Q. Okay, which one is the Q or conclusion? Okay, just follow this. Q whenever P. Okay, first one is conclusion, second one is hypothesis. Okay, so out of the two, the home team wins and it is raining. Which one is conclusion? Exactly, home team wins is the conclusion and it is raining is the hypothesis. Okay, and that's what I have done here when I write it in if P then Q form. Okay, so always whenever you have to find converse, contrapositive, or inverse, you should know there are two things you should know. One, what are the different equivalent forms of writing if P then Q? Okay, and second thing is you may write that condition statement in that form. Okay, after that, now finding the inverse, converse, and contrapositive is very simple, right? What is the converse of it? Remember what is converse? Converse simply means flipping the conclusion and the hypothesis. Excellent, Dhananjay. If the home team wins, then it is raining. Oh, I start with contrapositive. Okay, so that is correct. If the home team wins, then it is raining. Okay, what about contrapositive? Contrapositive is flipping the hypothesis and conclusion and taking their inverse. Okay, converse was if home team wins, then it is raining. Now you need to take the same flipped version, but for contrapositive, you also need to take negation. Excellent, Shreya Dhananjay. If the home team does not win, then it is not raining. Right? And what about inverse? Dishan, you can also give a try so that you understand what is an inverse. Okay, home team does not. Okay, now I am talking about inverse, the last one. Okay, what about others? Class, are you able to follow it? I'm just getting the replies from a handful of people. Is this clear? See, there are two steps to it. One is always bring down the conditional statement to if then P form. Okay, then following it is very simple. Okay, you just need to flip the conclusion hypothesis or take its negation. Yes, class, is this clear? Okay, good. Is this clear to anyone? Anyone it's not clear? Okay, I'm no hurry to rush up to other. It should be clear. Is this clear to everyone? Or should I repeat it once? Plus, I cannot see your faces. Please say yes or no. What about others? Okay. Okay, so I assume it is clear. Please, if it's not, just stop me. Okay. Okay, so let's move to now the last logical operation, which is known as a biconditional statement. Okay, and we'll end up there. Now, what is a biconditional statement? We already saw what is a conditional statement. Okay, now what is biconditional statement? Even if you didn't know, you can easily guess it's going to be two directional, right? So it's biconditional. So it's talking about something which is involving two directions. Okay, so let us see what does it mean. So if you have two propositions P and Q, the biconditional is first of all represented by a double-headed arrow. Okay, and what does it mean? It simply means it's named as P if and only if Q. Okay, so normally you have if P then Q, right? When we have a single implication, but here it means P if and only if Q. Okay, and in other words, what it means is it is the combination of if P then Q as well as if Q then P. Okay, it's a combination or bidirectional implication of both the implications when you take one of them as hypothesis and other as the conclusion. Okay, in general, how does its truth table look like? The biconditional statement is true whenever P and Q have same truth values. Okay, so if they have same truth values, okay, whether it's true or whether it's false, it's going to be true. Okay, but whenever they have different values, then it's going to be false. Okay, so how do you make the truth table of biconditional statement? A biconditional statement between the two propositions is always true when the two have the same truth values, and it is false when they have different truth values. Okay, sometimes it's also known as if and only if. Okay, so any thing that hits your mind when you see this, any of the operations which we studied, which is very closely related to what it is. Okay, here we have when the values are different, then it is a true, and when they are when it is same, then it's true, and when they are different, it is false. Any operation that we saw is kind of complementary to it. Yes, class. Any operation we saw is complementary to it, wherein when the two were same, it was false, and when the two were different, then it was true. Okay, so in other words, this was false, this was true, this was true, this was false. Anyone where we had this kind of truth table? Excellent, Usad and Rohit. Exactly, it is. It was Zor, right? Zor is true when the values are different, and it's false if they are same. Okay, so Zor is exactly the complement of biconditional. Okay, and biconditional actually is also known as XNOR, right? In terms of logic gates and all, it is your XNOR. Okay, so XOR complement is your biconditional. Okay, in XOR, whenever the two values are different, you have true, and whenever they are same is false. Whereas in biconditional, the vice versa is true. Whenever the two values have same truth value, it's going to be true, otherwise it's false. Okay, so let's see some equivalent versions of how biconditionals are written. So sometimes it is written P is necessary and sufficient for Q. Okay, so if you remember, when we had P implies Q, one of them was a sufficient condition and other was a necessary condition, right? But now when we write P double implies Q, since it means both P implies Q and Q implies P, so both of them are necessary and sufficient condition for each other. Okay, so basically when we say P implies Q, it is actually same as saying P implies Q conjunction Q implies P. Okay, you can check it for yourself. You make the truth table for this and this, you will see they are equal. Okay, so P by implication Q is exactly same as if P then Q and if Q then P. Okay, if both the conditions hold, only then the by implication also holds true. Okay, is that clear? Yes, class, is that clear? By implication statement. Okay, someone raised a hand. Please let me know what is the question. You can unmute yourself. Okay, that's fine. Okay, so is it clear? So I'll stop there. We can continue with truth tables maybe next time. Okay, is this clear, class? Or maybe let me end on this one since it would be kind of related. Okay, so in general, so we saw all these different connectives, right? We saw conjunction, we saw disjunction, we saw conditional statement, right? We saw conjunction, we saw disjunction, conditional, biconditional statement. Okay, so in general, all these different connectives are used to make your complicated compound statements, right? So so how do you verify, what is the value of a compound statement? Okay, so you can do that using truth table. Okay, so there's a very simple example of truth table that they have given here. So you have two simple propositions. P or not of Q implies P and Q. Okay, so how do you solve such compound propositions? Okay, so as I had mentioned yesterday, you can do this using truth tables. Okay, so in truth tables, what you do first, you look at the statement, compound statement, and see how many input does it have. Okay, so first step you should always do is check the number of inputs. Okay, once you know the number of inputs, assuming it's n, then you write all possible combination of those inputs. Okay, how many combinations would be there if I have n inputs? Yes, class, how many combinations would be there if I have n inputs in general? Very good. It's 2 to the power n, right? So you write all those combinations. Okay, you write the input. If it's 2, you write 2. If it's 3, you write 3 of them, and write or list all the possible combinations. Okay. After that, Whatever are the primitives which you require for finding the proportion, write them. Like you require a knot of q, so you write knot of q, and then try to find the value of your primitive propositions in this compound proportion, like p or not q and p not q. Okay, now once you have both of them, you can consider this joint primitive statement as one statement and this joint statement as one statement, and simply follow the table of implication. Okay, in implication table we know that it is false only when first statement is true and other is false. Okay, otherwise it's always true. Okay, and that is how you can find the composition or the truth table of your composition or the compound state. Okay, so what I want you to do is make the truth table of this. Okay, p implies q and q implies p. Okay, so it would require two inputs, p and q. Okay, and maybe you need to find p implies q, q implies p, and then take and of these two columns. Okay, and then check whether it's equal to this. Okay, and I'll listen from you tomorrow whether it was equivalent or not. Okay, so in tomorrow's lecture we'll throw more about compound propositions. How do we see they are equivalent, and what are different variations of these propositions. Okay, so I'll stop there, but please do try out this, and I'll also be releasing your tutorial, so you can also complete that over this weekend. Any questions, class?